While this is an online review session, it's intended for Kentucky audiences. Space permitting, we welcome students from other areas. We will do all we can to provide every student with equal opportunity to learn. During the session, we encourage participation. Please know that any participant causing disruption to the session will be removed. Also, AP is a trademark registered by the College Board, which is not affiliated with and does not endorse this product. Advanced Kentucky is your host. I'll be moderating. Again, I'm Michael Marshall, Access to Algebra Content Manager. I'll be checking the chat and letting Amy know if anyone has any questions, so she can
correcting me when I mess this up.
and concentrating on her presenting. Some etiquette for this: please mute your microphones, have your videos off, but you can use the chat button to get our attention. And again, I'll be monitoring the chat. We also are recording today's session. I just started that, and recordings, links to the handout, and information for all future content review sessions can be found by visiting this bit.ly address. And with that, I'm going to hand it over to Ms. Cash, and I'm going to sit back and watch the chat.
Okay, I'm going to steal the screen. Well, here we go. So if you could, well, hold on, geez. I don't want to share, I want to present. Here we go. You could just drop your first name in the chat and the name of your school. Like Michael said, I'm at Bowling Green High School, and we were in cohort 2 of Advanced Kentucky. So he's fancier than me. I've been teaching calculus since then, and actually go all around the country, not just in Kentucky, to do these review sessions with kids. And I really miss going live, to be honest. So you know, hopefully we'll be back live soon, but I'm glad to be here today. So if you'll drop your name in the chat. I'm going to pull up PowerPoint. Okay, get out of my way. This little bar is in my way. Go away. All right. Okay. So why can I not see the chat, Michael? Is it because I'm sharing?
No, you should be able to see. You just have to go up to the little 3 dots on your little status bar that's kind of hidden and hit chat, and it should pop up.
Okay, well, there it is, 3 dots. Okay. You know, Google Meets, Zoom, whatever, all the things. Okay, so Emily at Wilmot Union High School. Oh, first year ABBC teacher. Welcome, Emily. That's awesome. Naomi's Frederick Douglass from Lexington. Geraldine, is it Geraldine? I hope I got that right. From New Jersey. Welcome. Is it Sina or Sina? Potomac High School. Welcome. I don't know if I said it right. Paris, Redland High School in Pennsylvania. Gwen at Frederick Douglass. Welcome, everybody. Sina. Thank you for the phonetic spelling. I appreciate it. Okay. All right. So glad to see you all here today. Close that out. We are doing parametric and polar functions. We're going to start with parametric. Hopefully you have the handout and you are ready to go, as am I. Let's we're going to straight into it. We're going to talk about parametrics and polar. I'm going to do my best to go between my PowerPoint and my DocCam and some Desmos and all the things. Let's talk about our objectives today. We have, we want to look at calculating first and second derivatives of parametric functions with respect to time. Determine the length of a curve in a plane defined by a parametric set of functions. Calculate derivatives of vector valued functions. Vectors and parametrics, they're like best friends. Determine the particular solution, give it a rate vector and initial conditions. Determine values for positions and rate of change in problems involving planar motion. Determine a particle's displacement and total distance traveled over a given period of time. Calculate derivatives of functions written in polar coordinates. Calculate areas of regions defined by polar curves using definite integrals. Now, before we go on, I've just read all these things off and you're looking that on screen. So I'm going to give you a scale, go 1 to 5, 1 being I have no clue what all that means, to 5, I could teach it to a calculus student who hadn't had it yet. So in the chat, drop 1 to 5 on how you feel. And listen, it is okay if it's a low number. That's why we're here today. All right. Oh, 3 is good. 1.5. All right, that's fine. I'm going to tell you, my students saw that. They would all be down at the 1 level because we haven't even hit this yet this year. Okay, we got a 4. All right, 3.5. All right. All right. Well, the goal is to improve that number by the end of this session. Okay. And you know, this is a lot of math speak in here. And I'm going to tell you that as we go through, you're going to be like, oh, wait, I'm not a 2 on that. I'm definitely a 3 or a 4 on that. I've seen that before. I can do it. All right. When we get all math speaky, it gets to be a pain. All right. So what do you need? If you can have the handout printed, that would be great. All right. It is in that, was it it's a bit.ly/math CRP, I believe. And if you really need Michael to drop it in the chat, I'm sure he would. And a graphing calculator would be fantastic. Something to write with, obviously, and just like a really good attitude. I know for us people over here in the central time zone, it's a little earlier. I don't know if any of you all were even farther west. But you know, calculus on a Saturday morning, one of my favorite things. So here we go. Parametric and polar functions make up to 11 to 12% of the AP Calculus BC exam. That information comes straight from the AP College Board, AP Calculus, AB and BC course and exam description, straight from them. So 11 to 12% of the BC exam will be based on these topics. Now, the thing about these topics is they include a lot of other topics that you learned earlier. So it's the context. So what I'm going to have you do is just go to this Quizlet real quick. I'm going to drop this in the chat. Let me get it real quick. Where'd my chat go? Okay. This is just a little flashcards. I'm going to let you have 3 minutes. Just go run through the flashcards and just to look at the notations and the things that you see. It's just a flashcard that there's not any grading to it or anything like that. So go 3 minutes. Okay, so hopefully we're finishing that up and getting ready to come back in. We're getting ready to start mini lesson number 1. Hopefully everyone's back. Okay, so mini lesson that we're not going to go straight through the handout. So we're going to do mini lesson, then we're going to go do some multiple choice, and mini lesson, multiple choice. And in between those, I'm going to do some examples that you do not have in your packet. And the reason I don't have them is because I want you to watch what I'm doing and focus. I don't want you to be writing or anything like that. Okay, so the first mini lesson is defining and differentiating parametric functions and finding arc length. Okay, if you've got a smooth curve given by 2 functions, x is your horizontal function and y is your vertical function, then your slope, dy dx, is the derivative of your y function with respect to t over the derivative of your x functions with respect to t. That makes total sense. And of course, dx dt cannot be 0 because we cannot divide by 0 and slope would be undefined. Okay. The second derivative formula is the weird one. Now, we're going to do an example of it in a minute. You take the derivative of your first one, all right, but then you have to divide out dx dt again, all right? I'm not here today to explain why that is. That is something you need to remember, okay? And we're going to talk about the distractors that they're going to try to trick you with in the multiple choice, so be careful there. And then the third one, length of an arc for parametric graphs is s equals the integral from a to b, the square root of x prime squared plus y prime squared. Okay, now listen, that formula works when the curve does not intersect itself. All right, and the curve also must be smooth. All right, because why must it be smooth? Because if the derivative doesn't exist, then this integrand does not exist. Okay, so it has to be smooth. So before we move on, I have in the next screen these example problems that I'm going to do on my document camera. All right. So I've given you in parametrics, sometimes they give you the position X and Y, and other times they give you the velocity X prime, Y prime. You know, you have to do things depending on what your evidence is. Here, our evidence is x of t, y of t. And I've written those as separate functions here, but sometimes they're written together as a vector in those chevrons, you know, those pointy parentheses, I guess you'd say. One of my students called those vector entheses one day, and I've kind of adopted that in my class. But here they're written separately. It doesn't matter, okay? Something that I want to emphasize is you don't have to have a clue what that looks like to do this work, all right? Something that kind of makes my students feel anxious is they're like, when I'm working with functions and you give me, it could be a rational function, a logarithm, an exponential, I kind of have an idea of what that looks like. All right. So for instance, this x value, if that was y equals 3e to the 2x, you should have a good idea that what that exponential growth function looks like. Okay. Same thing here with the y, but you put them together and my student, they're like, I don't know what it looks like. And they're very uncomfortable. Doesn't matter. You don't need to know what it looks like. Okay. We're going to do 3 things with this position pair. We're going to write the equation of the tangent line at 0. We're going to find the second derivative with respect to x. And then we're going to write an expression that gives the length of the curve from 0 to 5. Okay. This is where, like I said earlier, you do not need to be writing. You just need to. Okay, let me get my stuff to come up. I got to go to my doc cam. Hello, Apple. What are you doing down here? Okay, hold on. Nope, I don't want to do that. All right, I'm just going to end the show for a second while I get down here and get my doc cam. Okay, can you all see my hand? Michael, can you see my hand?
Yes, sorry, I couldn't find the unmute. Yes, I can.
Okay, yes. Okay. All right. So we have x of t. We want the equation of the tangent line when t is 0. So tangent line, I need a point and I need a slope. Okay, so first my point would be x at 0, y at 0. So that would be, let's see, 3 times e to the 2 times 0, that's 3e to the 0, that's just 3. And then e to the 3 times 0 is 1, 1 minus 1 is 0. So there's my point. All right, but my slope, right, is that dy dt over dx dt. So my slope is y prime of t over x prime of t, which is, that's going to be 3e to the t, 3e to the 3t, excuse me, over 6e to the 2t. Okay, when t is 0, so I'm going to put my substitution line at t equals 0, all right, equals, when I put in zeros, these e's, these are 1s, so that's 3 over 6, that's 1/2. Okay, now let me pause for just a second here and talk about linking errors, because the things that I've learned since I was brought into Advanced Kentucky could fill a volume about things that you could lose points on and that you probably sometimes do without even thinking about it. Do you see my such that line with t equals 0? If I left this out and said equals 1/2, I am saying my slope is always 1/2, and that is not true. And that's called a linking error. A linking error is when you say two things that are equal that aren't, okay, or aren't always equal. All right. Mathematicians are very particular about what is equal and what is not. So just be careful, show your substitution, all right, or don't put equals, whatever. So we'll talk about that more as we go on. So my tangent line, y equals 1/2 x minus 3 plus 0. I know I don't need the plus 0, but there it is. You could also have, y minus 0 equals 1/2 x minus 3, whichever form of the line you like. It doesn't matter. Okay, done. All right, our second derivative with respect to x. So I have my first derivative right here. Okay, my first derivative is my slope. Okay, dy over dx. Now, before I take the second derivative, I'm going to simplify that. Okay, so dy dx, all right, is 1 over 2, and that's going to be e to the 3t over e to the 2t is just e to the t. So I have 1/2 e to the t. All right, and so my second derivative is the derivative of my first derivative, which is just 1/2 e to the t. But then you have to divide by dx dt again, 6e to the 2t. All right, which is, let's see, 1 over 12e to the t in the end. So if I were writing a distractor, and a distractor is the wrong answers, this is the first one I'd put right here. All right. Okay, I would leave out divided by x prime again. Okay, so be aware of that. Okay, you need to know that parametric. And those note cards that you just did on Quizlet, I'm a huge proponent of note cards, but I'd honestly rather you actually write them physically yourself. Get your note cards, write them physically, shuffle them up, go through them. All right. So on the one side, it might be second derivative of a parametric, and the other side, you'd write the formula, but also make some verbal notes about it. That would be a good idea. Okay, third one, expression for the length of the curve from 0 to 5. So we're going to integrate from 0 to 5 square root, and it's just going to be x prime squared plus y prime squared. We're going to connect this here in a minute to something you already know, but since we're here, this is dt because these are in terms of t. So integral value from 0 to 5, the square root, x prime is 6e to the 2t squared plus y prime is 3e to the 3t squared. If it were multiple choice, they may or may not clean that up, but be careful. Don't forget to square that's 36 e to the 4t, and this is 9 e to the 6t. Okay, but I'm not going to clean it up right now. Okay, so there are those. Go back to my PowerPoint. Okay. We are going to go into some breakout rooms now, just randomly. All right. And I want you to complete multiple choice questions 1 through 4 and discuss those with your partners. Okay. So talk through them. You might have 2 people, 3 people in a room. All right. These are non-calculators, so you're not allowed to use a calculator. Okay. And, but do 1 through 4, and then we'll bring you back in.
All right, I'm gonna open up the rooms. There's 2 rooms of 3 and 1 room's of 2 with Miss Cash in that one. But she'll probably jump around.
Okay.
Kelly, if you're having issue, you can ask me in the chat. There should be an invitation for you to join a room. There you go.
Hey,
Yes.
so why is it that on my Mac, you use a Mac, don't you?
Yes.
How come sometimes I can get the bottom to pop up my little taskbar, and sometimes it's like, no, not coming.
The little taskbar on
I thought I
what?
said it last week that no matter what I was doing, it would come up
On
there.
Zoom or on
Just
just like your
well, I guess
thing on your Mac?
I'm in PowerPoint.
Oh yeah. No, I don't know. I think mine's locked, or well, it was. I don't know. Again, everything got erased when I updated to the Big Sur.
Yeah, time's up. Bring him back. I don't think
Okay.
that's okay. How was
I
that
think
first one? Good.
what?
If I make a mistake, you need to yell. And
Oh
how
yeah, it was good.
was that okay?
Yeah, I think we lost some people in the breakout transition.
Yeah.
Yeah.
Okay.
There was one person that wasn't going and I asked if she needed help, disappeared.
Yeah. Okay. Okay. So we're coming back in. Oh, add. I think that Paris was.
Yes. I
having
just did it and I hit some. Oh, yeah, I got her back in.
All righty. Welcome back, people.
Okay.
Okay.
I'll be kicked back in 9 seconds.
Okay. Do we have something in the chat?
They just didn't mean to leave so early.
Okay. Good. And admit. Poor Paris. Okay. So we're going to go through the answers. If there's anything you want me to back up and discuss, just drop it in the chat and I will. All right. I don't want to, sorry, that's my dog. And there's a guy working in the front yard and she's going to freak out all day. And I'm sorry. So, but if I shut the door, then she'll freak out more. So I'm going to go through the answers. I didn't mean to go there. Go back this way. Okay, I'm going to go through, but if there's something you want me to go over, like finding the answer, I will. Absolutely. The answers are here, but they're kind of quick. But we want to maximize our time and get through. So here is multiple choice 1. The answer is C. All right. And that's all well and good. Hopefully you got C, but I want to point out one of the practices we do in my classroom is we talk about how distractors are made all the time. And I'm talking backing up into pre-cal and algebra 2 if I'm teaching it. We talk about what are mistakes that you might, and I'm like, at the end of a question, I'll be like, hey, what distractors might I write for this question? You know, what would be a good distractor? What do you think is the most common mistake? What else could happen? You know, I want them to think about possible mistakes to try to head those off because we're not really good at multiple choice. We just aren't. You know, the kids think they are. They think they're good because they say, oh, there's my answer. And I'm like, well, because you made the most common mistake. So, you know, they're like, oh, it's always a disaster when my kids would come out of both of my children took honors chemistry and they'd come out of class and they're like, I did so good on that test. And I'm like, oh, that's a guaranteed like D, you know, but they'd come out and they'd be like, that was really hard. I'm like, oh, you might've gotten an A or B. So that's just, you know, how it is. So let's talk about distractors. The answer is C. Answer A is kind of silly because it's not even a ratio. It's just, they multiplied them instead of dividing them. I just think that was kind of silly. But B, I think, is our best distractor. This is the person that forgot to do chain rule. All right. D is probably my thought second best, but maybe first. It's upside down. All right. So pointing those out, and one of the people in my breakout rooms, I can't remember who it was, that Kim or I don't remember, somebody said, you know, I tell my students they're always going to put the one that's upside down when you do those ratios. And you're probably right. That's probably the first one they write. Okay, so forgetting the chain rule here in D, in B, in D, it's upside down. C is the correct answer. And number 2, second derivative. All right, so finding the first derivative. Now, when we do first derivatives, I rarely simplify unless I just need, for some reason, rarely simplify. But if I'm going to do a second derivative, I simplify this because it's going to be so much easier. Now, these are 2 polynomials, they're cake derivatives. This is an easy simplification. We take the derivative of 3t minus 1, that's 3. But then we have to divide out dx dt again. So it's over 2t. See this distractor right here? This is the person that forgot to divide out x prime. All right. These 2 are just the second derivatives. I mean, they have done the second derivative of this one. I don't know where 3t minus 1 comes from. Oh, 3t minus 1 is the first one. Oh, this is the first derivative. They didn't read that as a second derivative. Okay. So looking at those distractors, B is the correct answer. Number 3, we want the tangent to the graph at the point where t is 2. All right. So they have to find the point and the slope. Sometimes they hand you the point. But here they gave us t. Now, I can't tell you how many times my kids have put 2 in for x and then, instead of t. All right. They are so used to the input being the x value. They kind of we have to, when we get to parametrics, we have to break that habit. Be like, no, t's the parameter. All right. You've got to find your x and your y. Okay. The x and y there is 5, 4. And then you find your slope doing dy over dx and subbing in. That is 8/5. Answer is C. I looked at these distractors, and so we obviously have some where 5/8. You see that where they put the slope upside down? And I didn't really work on many of the others. This 8/5 minus 12. And I'm not sure where the minus 12 comes from. All right, but they're all good. So next, number 4. Length of the curve determined e to the 2t and y equals 3t minus 1 from t, let's see, t equals 0 to 2. Hold on. Okay, and so the answer is D. Looking at these, all right, the answer is this one, D. In answer B, they forgot to take the derivatives before they put it into the formula. All right. In answer C, they forgot to square their derivatives. Do you see that? So here, see, if you take these squares off, you get answer C. All right. I'm not sure. I didn't put a note on part A, but there's 2 of them. The not squaring is a big deal. Like I hope they wouldn't put in one that was like 2e to the 4t, where you just forgot to square this 2 right here. I would hope they wouldn't put that in, because that's the one that would sneak in and get all of my kids. All right. And it is not a, it's not a computation test, so they kind of try to leave those out, hopefully. Okay, so moving on. Okay, our next mini lesson 2. So this is on, I believe, page 2 of your handout. Get to my page 2 of my handout. Okay, here we're looking at defining and differentiating vector valued functions and solving motion problems. So thinking of parametrics as motion, all right? There are those vector parentheses I was talking about, these chevrons, okay? Vectors can be in chevrons or parentheses. It happens both ways. It's mixed up, so I mix it up in my classroom, okay? So x prime is the rate at which the x coordinate is changing. Y prime is the rate at which the y coordinate is changing. So you've got a position vector, a velocity vector, an acceleration vector. All right, these all make sense. And then we have the speed of the particle, which is the magnitude of the velocity vector. And we have the length, the arc length. Now this is the same formula we just did. All right, so this is the distance traveled. So in the last one we just did, it's like the length of the curve. Here we're talking about particle motion, so it's distance traveled. Well, that's the same thing. All right, but I want to make some connections here to AB calculus. So let's move to the next slide. Okay, so in early calculus, S of t is our position function. Okay, in parametric calculus, S of t is a position vector. It has two pieces. All right. In one-dimensional motion, velocity is the first derivative of position. Same thing, velocity, but it's a velocity vector. It has a horizontal component and a vertical component. Acceleration is the first derivative of velocity. Acceleration is the derivative of velocity. Again, it's a vector. It's two components. All right. Speed is the absolute value of velocity. Okay. Now, depending on how much vector work you've done, speed is the magnitude of the velocity vector. Okay. Do you see these double bars? That means the magnitude, all right, of the velocity vector. All right. And this is just the Pythagorean theorem. It's all it is. All right. And I'll draw that here in just a minute. So over here, distance traveled in one-dimensional motion is the integral of the absolute value of velocity. All right. Now, we don't normally write it this way. That's the integral of speed. Do you see that? Distance traveled is the integral of speed. Okay. So distance traveled is the integral of the magnitude of the velocity vector. We don't ever write it this way because we don't really write things in that vector notation, but that's what we're doing. This is our speed. Here's our speed. Here's our speed. This is two-dimensional. Hold on. I'm sorry. No, stop. Oh, okay. Hopefully she'll quit. All right. Do you see that? Do you see that connection there? Okay. All right. So I'm going to go and I want to do some sample problems again with you. Okay. But before I do that, let's just talk about that whole magnitude thing just being the Pythagorean theorem. Okay. So get my document. This is what I'm talking about, Michael. It does not want. What did I do? It will not let me see my taskbar. That's annoying. Okay, so when you have a velocity vector, say v of t is 2, -5. All right. So what that means is your horizontal motion is going to the right to, we just say meters per second, right? And your vertical motion is going down, we'll say 5 meters per second, okay? The magnitude of your velocity vector is this hypotenuse of that right triangle. These are always perpendicular, so you always get a right triangle here. So if this is 2 and this is -5, right? Then my speed is the square root of 2 squared plus -5 squared. All right, square root of 29. All right, it is just the Pythagorean theorem every single time. All right, but if you haven't done any vector work and you just see a formula, it's kind of hard to understand, but that's all that's happening there. Okay, so we're looking here and we have this time, instead of giving you position, I have given you velocity. All right, make sure I'm on the right one. I want to make sure I'm on the right. Okay, I'm not, I'm on the wrong page. That was the next one. We don't want to do those yet. It's like, wait a minute, we haven't talked about this yet. Did I not print this one out? Oh, wait, yeah, it is the right one. Geez, Amy. Sorry, second guessing myself. Here we go. Okay, so this time, this is my velocity vector. Should say vector, and here it does on the PowerPoint. Okay. So my horizontal rate is 3 constant, and my vertical rate is -4t. And I gave you the position of the particle is 5, -1 when t is 2. Okay. So I'm going to skip number 1. I'm going to go down. What's the speed of the particle at t equals 3? Well, my velocity at t equals 3 is 3. 3 times -4 is -12. So my speed is just the square root of 3 squared plus -12 squared. 144 plus 9 square root of 153. Easy peasy, done, right? Okay, this is what's the acceleration vector of the particle at t equals 2. Well, the acceleration would be x double prime, y double prime, which would be 0 and -4. So this is acceleration does not have a t, so that's at all times, okay? And so you could say I have 2 here if you wanted to name it. Acceleration at 2 is 0, -4, but it's that all the time. And it says, what's the distance traveled by the particle from 0 to 10? That's the integral of speed. So from 0 to 10, the square root of my velocity. Don't take the derivative. This is already x prime, y prime. So this is 3 squared plus -4t squared dt. Okay, that's the distance traveled. Okay, so remember the distractors. So in the last one, in order to do this, we had to take the derivative to put it in. Okay, here, these are already derivatives, and I named it x prime, y prime, but if they just said my velocity vector, say they put it like this. Okay, I can imagine somebody saying, taking the derivative of this to put into this formula. No, this is x prime and y prime, and we already have those. Okay. All right, let's go back to this first one, the position of the particle at t equals 0. And something I didn't put on that last slide that I kind of wish I had was displacement. So let me slide down here. And so displacement in one-dimensional motion is the integral of velocity. Okay, that's something you should know cold. You should have that one down. All right, so displacement in parametrics is just the integral of velocity again, except there's 2 pieces. So in parametrics, it's the integral from a to b of x of t and the integral from a to b of y of t. That's my displacement. Okay. All right, now here's the difference. The displacement here has 2 components. So sometimes they might ask you for the magnitude. Listen to me, the magnitude of the displacement. That's how far you've gone, right? How far away you are from where you started. It doesn't matter, if you went right, left, up, down, how far are you from where you started? Then you would use Pythagorean theorem. Whenever you see magnitude, it's Pythagorean theorem on a vector every single time, okay? So this is horizontal displacement, comma, vertical displacement. All right. And so the entire displacement would be take these and do the square root of this one squared plus this one squared. That's how far you are from where you started. All right. Yeah, and that's the distance formula too. Right. So if you knew you started at 5, -1, and then you ended up wherever, it's just distance formula between the 2 points. Okay. But let's find the position of the particle at t equals 0. All right. So I know my position at 2 and I want my position at 0. So I'm going to do them separately. X at 0 is what I want. X at 2 is what I have, plus the integral from 2 to 0 of x prime, which is 3. okay? Exit 2 is 5. So this is 5. This is plus 6. This is 11. Okay. All right. So that is my new X position. Then I'm going to do my Y position. My Y of 0. This is just fundamental theorem here. Equals Y at 2 plus the integral from 2 backward. Whoa, 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 whoa. I messed up. Anybody see where I messed up? Right there. Nope, 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 nope. It's -1. Okay, I'm going backwards. I'm at 2. I need to go back to 0. Do you see that? Okay. 2 backwards to 0 of -4t dt. Dot, dot, dot. I'm not going to finish that one. But again, here's the thing. If I'm using my calculator, I don't care what order this is in. I just put it in like it is. So y of 2 is, this is -1 plus the integral from 0 to t of 2 to 0. Just be careful with that because it's backwards. You'd have to subtract it if you came up with a number. Okay. So hopefully that was helpful. Go back to the PowerPoint. Play from the current slide. So we're going to go and do some more multiple choice questions in your breakout rooms. 5, 6, 7, 8. 5 and 8 are non-calculator questions. 6 and 7 are calculator active questions. We will talk a little bit about the calculators when we come back, and we're going 6 minutes again.
Okay, we got a few. I'm gonna open the rooms. I might have to move some people around so that people aren't by themselves.
All right, just tell me when to start time.
Oh, okay, I got it. I'm moving them now.
Okay.
Oh, I can't hear you. Hold on.
I got you. Okay, now you can.
Okay.
You know,
Oh, I
like,
thought it was me.
if I go down to the bottom of my screen, there pops the taskbar. It's all fine. But then
Yeah.
sometimes I'll be
Yeah.
in here like, no.
I had to go into like preferences, like settings, and be like, lock it in place. Don't ever leave me.
I need you right there at the bottom.
Yeah.
I thought I did that, but obviously I didn't. Obviously, I don't know what I'm doing. Okay, we're almost there. Okay, that's it. Time's up. We're already at the end of the first hour.
I know. Are we taking a break or?
Yeah, we're gonna take a break.
Okay, you take the lead on that. Just tell me.
Okay, well, I'm gonna go over the answers real quick first.
That's fine. Tell me when to bring them back. Are they talking to each other or not?
I was only in the one group and I was talking to them. They seem to be talking to each other. Done with that page. I'm gonna have to go a little faster in the second hour.
Are you doing the reading? Do you do the reading? I never can. You didn't
I
apply.
still have never applied.
Yeah, I figured if you'd applied. I got demoted this year. I was table leader last year. Now I'm just a reader again.
Well, I can't believe they're letting you do it when you're not teaching.
They don't know that.
I got you. Well, I won't tell them.
Yeah.
I thought I was gonna apply this year and I forgot to do it. So I guess I'll apply next year.
I about said no. One, because I did get demoted, but I don't blame them. I don't feel I probably didn't grade enough. I was so busy back reading my people's, and they had so many questions that I just didn't get a lot of time to grade my own. I don't know. I used to get offended about stuff, but it's a mystery how they pick things. So I don't really.
Are they coming back?
I don't know. You didn't tell me to bring them back.
I did.
Bring them back.
Bring them back.
1 minute, 60 seconds.
I like LTF so much. I like working with teachers so much, and I hate grading papers. So I make more money at LTF.
Yeah.
And that's
well, I have to.
Those are college dollars for me. That's my kids' scholarship fund right there. Is all the NIMSY work I do. All of that goes into paying, so we have very small student loans. And so, but I feel like I would get more NIMSY work if I had read. I mean, I did do 5 videos this year.
Mm-hmm. Well, I've got to go right. I finally got a definite answer what I need to do with my last year's pay for reading. So I got to write my company a check, KSTC a check, and give it to them Monday.
That's right. You don't get to keep it.
No.
Do it on company time.
Which, I basically didn't. Half of it was in the weekend.
But I want to go to the reading. I don't want to do it online.
Exactly. And that's why I said yes this year. Just I was scared. If I said no, I might get forgotten. And I do want to go see my friends again. I know it's weird. It's math camp.
Yeah. Welcome back. Let's look at some answers. Okay. All right. I don't know if y'all can see that. Okay. So answer to number 5 is C. That's a pretty straightforward velocity vector. Take the derivative, sub in 2. Good one. Okay. Stop doing that. All right. Next. All right. Number 6, also answer C. Seems to be a theme here. All right. But this time, they gave you the velocity vector and you have to find the speed. So again, there it is. Pythagorean theorem. See that line. All right. Next. 7, calc active. This one is only one piece. And I find that in parametrics, a lot of times they just will ask the X position or the Y position at time 2. Okay. So there's your fundamental theorem hanging out. I wonder if the one without 2.7 is in there. In the distractors, it probably is, forgetting to add 2.7 to it. All right. Be aware, if you forget this, if you just integrate, you're just getting displacement. This one, I didn't really talk about in the prep, but you know, the describing motion of the particle at a given time. Is your particle moving up, right, down, left, whatever. And that is, if x of t is positive, you're going right. If x prime, not x prime of t is positive, you're going to the right. If it's negative, you're left. If your dy dt is negative, let down. If it's positive, up. All right. Very, you know, according to that vector like I drew earlier. Okay. So now before we start mini lesson 3, which is polars, all right, we're just going to take a short break because we are already an hour in. I know it's so exciting. You were probably like, you didn't even notice the time had passed. All right, but let's take just a little 5-minute change your fluid break. And we will be back at 10 after.
I'll be right back. 10 after, you say?
I'm sorry, what?
I said I'll be right back. 10 after, okay. I'll be right back.
Okay. Are we back? Hello. Let's see if everybody's here. Can you all hear me? Michael's not back. Okay, good. Thanks, Emily. Okay, so we're going to go a little faster to try to get all this in. Polar coordinates. Again, sometimes you don't have to know what these look like, but I'm not going to say that because sometimes you do. All right. If you have your calculator, you can be like, well, you can go to polar and do a polar graph, but that's never really necessary on any of the problems that they give you. But there's a couple of polar graphs they do actually need to know what they look like. All right. What should we know? Y'all should know how to change your polar form into parametric form. In this case, we're getting ready to find the slope of a polar curve. All right. And so we don't have a formula in R equals form. We have a formula in XY form. Okay. And it's dy d theta over dx d theta. All right. I do not know this formula off the top of my head. I sincerely don't. I just change it to polar form and then take the derivative of y over the derivative of x every single time. Okay. So looking at some example problems, you do not have these. This is what is the slope of the line tangent to the polar curve r equals 1 plus 2 sine theta at theta equals 0. I really think that many of my students would mess this up. All right, so you all don't need to do this. Don't do this. This is where I would be, warning them off. Okay, they would find r prime and put 0 in. But r prime is not the slope. That's the rate of change of r. Okay, that is the rate of change of r. Let's talk about that for just a second. Let's go into, that's the wrong one. Sorry. Go away, Quizlet. Another one. Oh, what did I do with it? Here it is. Nope. Exit that. Well, I want to go here to my polar rose. Okay, so I graphed this earlier on Desmos. Okay, see this polar rose. So R is the distance you are from the pole. So looking at, right here, this point right here, that is 1.1, it's 1.4 away from the pole. That's the distance 0. This is 1.4 at theta. It looks like at pi over 4. So that point, all right, is r theta, 1.4 comma pi over 4. All right. Now, r prime means the rate of change of that length r. It does not mean the slope at this curve. Okay. So another thing you need to think about in polars is, where does my curve start? This one is 2 sine 3 theta. So what I usually do is I put 0 in and be like, okay, 2 sine of 3 times 0 is 0. This one starts at the pole. The cosine ones usually start out at the end of a petal. All right. So just kind of knowing a little bit more and having a little bit of practice of actually doing some graphing by hand, even though that's not technically calculus, you need to know a little bit about how polar things are graphed. So we want the slope of the tangent line to the polar curve r equals 1 plus 2 sine theta at 0. Well, I have to change this to x equals r cosine theta. R cosine theta is my formula, which is 1 plus 2 sine theta times cosine theta. All right. And then y equals r sine theta. Y'all, this comes from the unit circle, not the unit circle, from circle trig. So cosine is x over r, sine is y over r. This is 1 plus 2 sine theta. Now for time reasons today, I'm going to put these into my calculator. Notice I'm putting them in the rectangular. I'm not switching to parametric form. I'm just going to put them in. My calculator doesn't know how to spell, so theta is going to be x. 2 sine theta, close, cosine theta. This is for time reasons because we need to move. And then here's my y. 1 plus 2 sine theta, sine theta. Okay. So my slope is x prime is my slope is y prime at 0 over x prime at 0. So my fraction, I need the derivative with respect to x. Now my y prime is in y2, so alpha, get my y2 at x equals 0, and then the bottom of y1 at x. Now you could put these in separately and do the ratio yourself, but that looks to be 1/2, and the answer in this one is B. Okay, so on a normal day, I would actually probably distribute that cosine and take the derivative, distribute this sine, take the derivative, and then do the ratio by hand. That's a lot of times you have to do that by hand. Okay, now the second question I have in the example is, if a bug is traveling along the polar curve at time theta, is the bug moving towards the pole or away from the pole at t equals 5 pi over 6? So I'm looking at this R, and my bug is it's in motion. It's traveling along the curve. Okay, so we're switching our formula to a t because it means time. It really doesn't even matter. All right, so I need to know, well, what is R at 5 pi over 6? Well, that's 1 plus 2. The sine of 5 pi over 6 is 1/2. So 1 plus 1 is 2. So I'm 2 units away from the pole being the origin. Okay. I do actually know what that looks like, but you probably don't. All right. And that's all right. But now I need to know, you're like, well, I need to know my motion. So I've got to find R prime. Okay. R prime of theta, just plain, is 0 plus 2 cosine theta. All right, so what's R prime at 5 pi over 6? Well, 2 cosine 5 pi over 6 is negative root 3 over 2. So this is negative root 3. Okay, so because I'm at a positive 2 and R prime is negative, I'm moving towards the pole. Now, I want to talk about why I have to know both of those things. Why didn't I just find R prime and say, well, it's negative, so it's decreasing? Well, you can't say that because, let me go back to my Desmos screen. Where is it? Okay. All right. Here's the thing. You might be in a negative position. If you're in a negative position and your R prime is negative, you're getting farther away from the pole. All right. So this curve, it curves up and down. But when I get, if you see this, it's going to curve down here. All right. So these are because my R's are negative. The reason it graphs in quadrant 3 before it graphs in quadrant 2 is because my R's are negative, and they're going to curve down. I think I didn't draw this one out. But if my R was negative and getting more negative, you'd be going farther away from the pole. All right. When we do this in rectangular motion, what we talk about is a particle that's like horizontal on the x-axis. Think of it this way. If you're on the x-axis, if you are, my little bug is here, so he's at, say, -3, and he's moving left, he's going away from the origin. But if he's +2 and going left, he's going towards the origin. Do you see that? So when I ask going towards or away, I have to know 2 things. I need position and rate of change. If they are the same size, same sign, both positive or both negative, you're moving away from the pole. If they are opposite signs, you're moving towards the pole. So for instance, if this was negative, if I was at -2 and my rate was -√3, I'm negative and getting more negative, I'm moving away from the pole. I hope I didn't like totally confuse you there, but those show up, and it's a really simple kind of idea if you've done it. So here's the thought I try to plant in your head. If they are the same sign, they're working together, so you're increasing. If they're opposite signs, they're working against each other, you're decreasing. Okay. All right. Whew. That was quick. All right, but let's just take real quick and just take a few. We're going to take, it's 9 and 10. So I'm going to cut that down to 3 minutes. If you want to go to your breakout rooms and do questions 9 and 10, they are non-calc. So if all you can do is do the setup, that's fine. All right, but let's do the setup and then we'll come back and look at the answer.
Send them to the breakout rooms. Open
Breakout
the
rooms. Yes, breakout rooms.
Okay.
Just for 3 minutes, Michael, because we're going to.
Okay.
Get it all out? Is it all gone? Did you kill the duck? Is it all gone? Can you see my screen?
Yes.
Is this where I'm supposed to be to fix my dock?
Let's see.
It's on the bottom.
So show indicator, automatically hide and show the dot. Automatically, yeah, maybe that's it. Automatically hide and show the dot.
Where is that? And just
The-
click this.
Maybe, yeah.
Okay, see what happens when I do that. Okay. Now let's play. Okay, but see, now it's not there.
Oh.
All right, curse words, curse words, curse words. Okay. See, now it is. So if I guess if you're in a presentation, it's not going to be over the top of it.
Oh, is it not? Maybe. Yeah, I think no.
All right, show recent applications, show indicators for open, automatically hide, show, automatically animate opening, minimize windows. Refer to. All right, that does not help me. Okay, whatever. Okay, go ahead and click him to come back in because there's only 15 seconds left.
Okay. Close the rooms.
Yeah. I always run out of time. Well, Gwen's back. Hi, Gwen. Welcome back, Paris. Felicity. I love that name, Felicity. I think my niece had that American Girl doll. Looks like we're coming back. Okay, good deal. Oops. All right, so I have the first answer up. That is a straight derivative. All right, it's not slope. Remember, r prime is not slope. It's the rate of change of r. Okay, and you just substitute in pi over 18. That one, you have to know your unit circle. Okay, is what it is. Next, this one is a lot more. Okay, so we have answer D. Here is y prime on the top. Here is x prime on the bottom. You know, you can either use this rule, but like I said, I just changed x equals r cosine theta. Let me just show you my work real quick, as fast as I can on my doc can. Here it is. Okay, so see this? I find my x, I find my y. Derivative of y, derivative of x. Notice I didn't simplify anything here, nothing, because all I'm going to do is sub in pi over 2 and figure out all the numbers. That's it, okay? I do not know that formula off the top of my head, and I refuse to learn it because this is how I always do it. All right, so you need to be able to change a polar into a parametric to find the slope. That is not optional. Okay, back to the screen. All right, and there it is. You can memorize the formula if you want to. It's not wrong. I just don't know it. All right, talking about number 4. Here we're doing area bounded by a single polar curve. Okay, so the formula is 1/2 integral from alpha to beta of r squared d theta. Y'all, this does not have a pi in the formula. Y'all do not put pi out in front of that because it's not there. Where is the pi? Well, the pi shows up in your angles right here. You're like, shouldn't I feel like I need a pi there? No, this is not a circle. All right, we are not doing rotations. So that's one of the things that my students do is they tend to put pi's there. All right, so these are polar curves that you should recognize. Now, I'm not saying you should know them off the top of your head, all of them, but there are a couple here that you should. And so if you want to pause, this comes from Be Prepared for the AP Calculus Exam by Howell and Montgomery. It's a review book. All right. This circle in polar form is r equals the radius, whatever your radius is. Okay. This circle in polar form and this circle in polar form. These 3 circles here in the top. It's nice to know these lines too, but whatever. Y'all, and this is a secant theta. That's how I usually would write that, this last one. But these 3 circles are ones that they will give you in multiple choice without a drawing, without a calculator, and expect you to know them, okay? Down at the bottom, the limacons and the roses and the lemniscates, they generally give you those pictures. So like I said earlier, when you all don't need to be nervous if you don't know what they look like. If they're a complicated one, it's not going to matter, okay? But those 3 circles on the top, they do expect you to know those. All right. So if you want to pause and take a picture of that real fast, I'm going to give you about, 5 seconds to do it. Or you can look up that. That's a good review book. Okay. All right. So here's my first example. You don't have this one. Which of the following gives the area of the region enclosed by the loop of the graph, the polar curve r equals 4 cosine 3 theta, shown in the figure above? Okay. So you're like, what's different about these? Well, here's the thing. What can we eliminate? All right. Well, it's 1/2 integral from alpha to beta r squared d theta. So anybody who's not squared is out. So A is out and B is out because neither of them are squared. So see you later, guys. Okay. So it's 1/2 r squared. Well, if I square this 4, I'm going to get a 16. But if I have to take out half of it, it's going to be 8. So D is now out. And I have to decide between C and E. And what's different about them? Well, they're limits. Is it negative pi over 6 to positive pi over 6? Or is it negative pi over 3 to positive pi over 3? Okay. Actually, oh shoot, it still could be the 16 one. Hold on, we might have to double it. Okay, so here's what you need to do. I'm like, where am I when theta equals pi over 3? I'm going to do the top one. So it's cosine, so it's even. So negative pi over 3 and positive pi over 3 are going to give me the same thing. So 3 times pi over 3 is pi. Cosine at pi is -1, right? Times 4 is -4. All right. So when I am at negative pi over 3, I'm at -4. Y'all, this is +4. -4 is over here. And when I'm at pi over, nope, that doesn't make any sense. Pi over 3 is in first quadrant. If you graphed it negative, it would end up in third quadrant. Doesn't make any sense. Do pi over 6. 3 times pi over 6 is pi over 2. Cosine of pi over 2 is 0. 4 times 0 is 0. That would start at the pole, which makes sense here. So if I start at the pole and I end at the pole, all right, they have to be zeros. Do you see that? So it looks like it's going to be our pi over 6s. All right. So I know they're not using half a pedal because of the symmetry there. I know if I put in negative pi over 6 and positive pi over 6, I start at 0 and I end at 0. Okay. That answer is E. That one's kind of a weird one. I mean, here, but notice that even if you're like struggling, you can eliminate a minimum 2, but yes, actually 3 of those answers. All right. In D, they forgot the 1/2. Now, be careful about that because sometimes they'll use symmetry, right? So what if they'd only gone from, say, negative pi over 6 to 0? Well, then they're only doing half a pedal and then they would double it. Does that make sense? All right. But because of the symmetry here, I know they're starting at the pole and ending at the pole. All right. Practicing on graphing those is going to help you so much. All right. Here's another one. This is a lemniscate. All right. And this is where lemniscates are given in R squared. You don't have to know how to look. They gave you the picture, right? Thank you. That's nice. All right. So this one, when we integrate it, we get the integral 1/2 the integral, and we don't have to square this one. Do you see that? It's already squared. Does that make sense? But what do we have to do? We have to figure out the limits. Well, how do I do that? Y'all put in 0 there. Cosine of 0 is 1. We start at 18. So at angle 0, I start out here at 18. And what I want to know is when do I get to here? Because I'm only going to do the area on this half of that pedal. Okay. All right. So I want to know, I know I start out at the tip at 18, and I want to know when's the first time it's going to hit 0. So I set this equal to 0. All right. Well, cosine is 0 at pi over 2. So 2 theta equals pi over 2. Solve for theta, it's pi over 4. All right. I feel like I'm going to have to show you that. So let's, non-cooperative computer. So I have 18 cosine 2 theta. Okay. R at 0 is 18. So when your angle is 0 degrees, you're out at positive 18 as your distance. Okay. And then I want to be like, well, when does it hit the pole first? So 18 cosine 2 theta equals 0. So divide by 18. The first place that cosine is 0 is, we only want the first one. We don't care about the others. The first one is at pi over 2. So 2 theta equals pi over 2, divide by 2. Theta is not pi. Y'all, pi over 2 is not pi. It's pi over 4. Okay? So I know I'm starting, so, I have my little lemniscate, which looks like an 8. I'm starting here at 18. I come here at pi over 4. I'm here, and I'm going to integrate from 0 to pi over 4 of r squared, which, oops, that's r squared. Oh, it's still going to be 0. It doesn't matter, square root. Okay, so of 18 cosine 2 theta d theta. But I'm going to multiply this times 4 because I want the whole area. All right, but I'm only picking up half of that right-hand side. All right. Whew. Back here. All right. I don't remember that answer, and I do not have time to finish that one. If you want it, shoot me a message. Okay. So let's try 2 questions. All right. Use a calculator if you want. All right. Even on the non-calculator one for evaluation, but see if you can set them up. We're not going to go to breakout rooms. That's taking a little too much time. So like work on 11 and 12 on your own, and then we'll come back. Okay, you don't need a calculator on the first one.
Oh, sorry. Are we opening rooms?
No, I'm not doing it because
Oh.
it takes too long. We're just taking a few
Okay.
minutes to do these.
Okay, never mind.
Okay, hopefully you've looked at them. Even if you're not finished, we're going to move on. All right, on this first one, here's what I want you to know. So when I do that lemniscate problem, I feel like I'm scaring you all to death. You're like, I don't know how to figure out the beginning and the end. Oh my gosh, I'm going to die. And all these polar problems, I cannot do them. I understand. But y'all, look at these limits on all 4 answers. They're all the same. I don't need to know it. Okay. Now, this is a limacon. All right. You don't have to know that. I know that. But what they're saying is 0 to 2 pi is going to get you all the way around it. All right. So who am I eliminating? I'm eliminating A and B because the R is not squared. All right. Now look at C and D. Look at distractor C. Look what they put in the front. It's not pi. It's a half. This answer is D. That's an easy area problem. All right. 1/2. There's no other possibilities. A and B didn't square the R. There is no pi in front. It can only be D. I don't have to worry about the limits. All right. So that one's not too bad. And a lot of times they tell you the limits, like in number 12. Here we have the polar curve. Here's my R, which you'd put in your calculator. But we only want it from pi over 2 to 3 pi over 2. Well, okay. So we would integrate, would 1/2 the integral from pi over 2 to 3 pi over 2, square the R and get the answer. The answer is C. Okay. So a lot of times they tell you where they want it. They're like, we want it from here to here. And you're like, well, okay. All right. And you just do it. Okay. Sometimes every once in a while, there's a one in there where you have to know about, how to find half the petal, kind of separates, the people who really understand it from who don't. All right. But a lot of times they're like these 2 and they're very doable. Our next is the same idea, except we have the area bounded by 2 polar curves. A lot of times here, you're going to have to do like an outside region minus an inside region. You've been finding areas like this since middle school, like where you had, say you had a rectangle and there were 6 circles in the rectangle and they shaded outside the circles and you had to find the area of the shaded region. You take the outside area minus the inside area. You've been doing this for a long time, but now it's in polar. All right. Here are some examples of what that looks like. Here's the first one. The figure above shows the graphs of the polar curves, r equals 2 cosine 3 theta and r equals 2. What is the sum of the areas of the shaded regions? There's a typo there. Y'all, This is one of the ones that you're supposed to know. R equals 2 is a circle centered at the origin, radius 2. That's what it means. It just means radius is 2. All right. That's one you should know without the graph. This rows, maybe not so much, but I need to take the area of my circle, which is pi times 2 squared, so 4 pi, and I need to subtract this guy. Okay. So again, I'm going to be like, all right, I've got 3 petals. I'm going to do half a petal. So at 0, 2 times cosine 0 is 2. The cosine ones start out at the tip. Where's the first time I hit 0? I'm going to set this equal to 0. And so 3 theta equals pi over 2. And so the answer is pi over 6. So to get this first half petal, 0, pi over 6 is when I hit this the first time. Okay? They're not going to ever be things that aren't on the unit circle. So if you just want to start subbing in, like do 0, then do pi over 6, then do pi over 4, and just see the first one if you're doing it by hand. All right. But this one is calc active. So I'm going to throw in my calculator, the integral from 0 to pi over 6 of r squared. And then I'm going to take that and I'm going to multiply it by 6 because I have 6 half petals. All right. And then I'm going to subtract that from 4 pi. So that would look like this. Okay. In my calculator, I'm going to integrate. Oh, helps if I show you the dot cam. From 0 to pi over 6 of r squared. And my r is 2 cosine 3 theta. Be sure to put the whole thing in your own calculator, on your own parentheses.
Amy, don't forget your 1/2 out in front as well.
Okay, yeah, but I'm, yes, thank you. Squared. Okay, so you aren't allowed to use the parentheses that the integral gives you. Those aren't yours, that's theirs. You have to put your own parentheses around that. Yes, and she's right, I gotta put 1/2 in the front. Let me go back.
I do it a lot of times at the end just to not have to do it
Yeah.
right now. It's so complicated. But when I do that, I end up forgetting it half the time.
So I get this. That looks familiar. Evidently my answer is pi. All right. And so I take 4 pi minus pi. It's 9.424. There it is, answer D. Okay. All right, now I'm going to keep my dot cam on. This is my second one. The area of the region inside the polar curve, r equals 4 sine theta, and outside the polar curve, r equals 2. They did not give us a picture. And that's because these are both circles. All right, we just saw the r equals 2. And let's talk about that 4 sine theta. This is where you have to know what it looks like. So r equals 2, remember, we just had that circle. You know, I'm going to draw it the best I can. There's my radius 2. Okay, r equals 4 sine theta is a circle with radius 4, and it's positive, so it's going to be up top. So I'm going to, actually diameter 4, excuse me. 1, 2, 3, 4. And it's on the y-axis. I know it's on the top because it's positive 4. Okay. So that's the picture that we want. And we want the ones that are, we want the area of the region inside the 4 sine theta and outside r equals 2. So going back to my picture, inside this circle, all right, but outside of this circle. So this little moon shape up here. All right. I don't even know my limits, so I have to find these two. So I have to take 4 sine theta equals 2. So sine theta equals 1/2. And this is going to make sense. Theta is pi over 6 and 5 pi over 6. See there and there. All right, so those are my limits. All right, and so I'm going to do my outside function minus my inside function. So it's going to be 1/2 the integral value from pi over 6 to 5 pi over 6 of my outside function, which is 4 sine theta squared d theta minus, and we could put this all in one integral, but I didn't. So whatever. 1/2 the integral from pi over 6 to 5 pi over 6 of 2 squared d theta. All right. So it's my outer radius. Let me get a different color. If I'm looking at just a little slice right here, that's my outside radius. So big R squared minus little r squared, my inside radius. Okay. But I picked that problem because they did not give you a picture. And like I said, you have to know how to draw those 3 kinds of circles. All right. The sine ones are on the y-axis. The cosine ones are on the x-axis. And the 4 is my diameter, not my radius. Okay. You can graph it with, you could use, just going around your circle and subbing in values that you know, but that is tough. So let's see, what do we have? So we have 16 sine squared minus 4. So look, all of these are out. Okay, so it's here to here, and you're like, all right. So I have 1/2 16 sine squared, and we've got pi over 6 to 5 pi over 6. There it is. All right. Now, me solving for pi over 6 and 5 pi over 6, if you can eliminate these 4 answers, you can be like, well, I'll just test it and see which one it is. Okay. But you have to know what it looks like to know that this is the right answer. Okay. All right. So multiple choice round numbers 13 and 14. So look at those two. Just take a look at them real quick, and then I'll go through them. Oh, look, I pulled the same one. 14 is the one we just did, except she has it separated. We'll look at it. Yeah, it's but different answers. So let's look at it anyway. Okay, for time reasons, I'm going to move on. Let's look at this first one. We want the area inside R1, and that's that circle. See this? This is one of those circles you should know how to graph. The diameter is 3, okay, and it's on the x-axis because it's a cosine circle. All right, and then this is the limacon, this guy right here. This is actually called a cardioid, okay, 2 minus cosine theta. We want the area inside the circle, but outside of this limacon. Okay, notice there is not a 1/2 in front of any of the answers, and that's because they've used symmetry. All right, so they're only finding the area of this top half and subtracting this little guy, and then they're going to double it, which gets rid of our 1/2. Okay, so we're going to go from 0. All right, my outside function is my R1. So from 0 to here, all right, 0 to pi over 6. No, that's not what she's doing. My brain lost it for a second. They equal each other at pi over 3. All right, do you see that right there? All right, so the inside one graph and outside the other is subtract the area from 0 to pi over 3 of the outside function squared minus the inside function squared. Okay, we don't want this last area right here. All right, we stop here. All right. Okay. Now, honestly, I would have taken that whole circle and found the area and subtracted just this little piece if it was like a free response question. The next one is the same exact graphs I just did with you, except look, the answers are all different than what we had earlier. Okay, so we had already found that these two are equal at pi over 6. Okay, again, notice none of these have a 1/2 in front of them. All right, so they're doing, instead of ours, which is pi over 6 to 5 pi over 6, what are they using? Well, they've got 0 to pi over 6. They're doing the outside separate from the inside, okay? And they're only going to do half of it. So using symmetry, set up the area of half, the right half, and double it. All right, so the right hand side, we're going 0 to pi over 6 of 4 sine squared. All right, that's this area, y'all. I'm colored, it's not colored in, that's this half circle, right? Well, it's not this half circle, it's just here, 0 to pi over 6. And then we're going to do from pi over 6 to pi over 2 of this circle. All right, so they're splitting it into 2 pieces. They're doing, I can't draw on that, so hold on, yeah, I can. So they're doing this bottom piece, 0 to pi over 6 gives us this little sliver, and then pi over 6 to pi over 2 gives us this little pi wedge. We add those together and double them. All right, there's lots of ways to do that. All right, but that's one. So this is not outer minus inner, because when we're going from here to here, we're only using this top circle. We're going from here to here, we're only using the r equals 2 circle. All right, what else might they ask you? They might ask you when a particle is at rest. Y'all, a particle is at rest when the velocity vector is 0, 0 at the same time. 0 at 0 at the same time. They might say, describe the motion. We've done that. When a parametric curve has its rightmost or leftmost point or highest or lowest point, those are just maximums and minimums on the y term or the x term. That's really not two-dimensional because you're only going to do one of them at a time. Okay, so that's just, set your derivative equal to 0. When a parametric has a horizontal tangent, so you're going to set your slope equal to 0, or a vertical tangent, you're going to set your slope where the bottom is 0. And then if a particle on a polar curve is moving towards or away from the origin, those are other things they might ask you. Okay. All right. Since we are short on time, we have about 5 minutes. I'm going to talk about free response 1. We have already done A, B. I want to look at C. All right, so looking at free response number 1. We've already written the equation of a tangent line today, so I'm going to let that one go. All right, the total distance traveled, remember, we've already done that as well. That's the integral of speed, but it's parametric speed, so we've already done that one. But let's look at C. For what value between 0 and 1 does a tangent line to the curve have a slope of 4? Find the acceleration vector at this time. So this is calc active. We want the slope to equal 4. So the first thing I have to do is find the slope. Well, that's dy over dx. And we're going to set it equal to 4 in my calculator. So I'm going to put cosine t squared over sine t cubed in for y1. And I'm going to put 4 in for y2. and I am going to find t. All right. And then I'm going to take that t and I'm going to find my acceleration. I'm going to take the derivative of these two at that t value. All right. And then it says find the x coordinate when t is 1. We have the x coordinate at time 2 is 7. So we've already done that one as well today. All right. Does anybody want me to show them part C on the calculator before I look at the answers? Okay, crickets. Okay, so let's look at the answers. Oops. Okay, so here is, the first right equation, tangent line. You need slope and a point. So you
Amy, I
find-
think someone does want you to.
Oh, okay, good. I'll go do it. Let me go back though. All right, so
Yes, please do.
please do. Okay, so show document. Okay, so come here, calculator. I'm going to put, listen, I never go to polar parametric. I do not change out of function ever on any of this. So I've got sine t squared is dx. And I have cosine, no, that's sine t cubed. Oh, to get it right. Cosine t squared is dy. Okay, so now this is dy. So, and I am going to, oh, I got to graph the slope. So I'm going to in y3, I'm going to do y2 divided by y1. This is my slope. This is dy over dx. All right, notice I turned off y1 and y2. That's what I did when I turned off those equal signs. I don't want to see those. I'm only looking, let's see, between 0 and 1. So I'm going to set my window 0 to 1, right? And when I want to know when that equals 4. So I want to know when that y3 is going to equal 4. So I'm solving for that intersection. Okay. Now, it's doing a derivative. That didn't take too long. So I'm going to find 5, enter. Okay, so it's 0.6164862. I need to hold that t. First of all, I'm going to write it down on my paper. And let's be clear about writing on your paper and FRQs. This is important that you tell your reader what you're doing. So you're going to say slope equals y prime at t over x prime at t equals 4. And then I'm going to put my answer, t equals 0.6164862, and I'm going to say equals a, so that I don't have to write that again. And let me get it, see if I'll do it. I'm going to go over here, and I'm going to pick up x, there it is, and I'm going to store it as a on my calculator too. All right. Now I need the acceleration, all right, at a. All right, maybe I should have used b, but a of a. Let's switch it to b. Because I use a at point b. Okay. Is, and then I have to tell them that that vector is x double prime at b, y double prime at b, which I'm getting ready to find in my calculator. All right. I cannot get points if I don't tell them what I did with my calculator. And I can't just say a of b because they didn't give me the acceleration, they gave me velocity. So I have to say, this is what I'm doing to my velocity to get acceleration. So on my home screen, x double prime, that would be the derivative of y1. Remember, y1 is x prime. So this is the derivative of x prime at x equals, and I stored that as a in my calculator. This is 1.109. This is where I round because it's my answer. And then I do the same thing, but this time on y2, negative 0.457. This is what I have to tell my reader. I have to tell them how I found my t-value. So this is my equation. This is the answer, right? And then how I found my acceleration subbed in, all right? Now you can round this and you can write this. It just, that is my habit, is to give it a name and not round it. Don't round it in your calculator until the end. Okay, that's how that is done. Right. Okay, so here is an equation for the tangent line. This is on, it says Calc Active, so you just stick this on your calculator, all right? And then you write your equation. Total distance, integral from 0 to 1, x prime squared plus y prime squared in a square root. Easy enough. You've already got 4 points and you really haven't done anything super hard. All right, here is C, what we just did. So the slope equals 4. All right. Now, remember on my paper, I said y prime at t over x prime at t. Those are interchangeable with these. That's fine. They actually put the functions. I put their names. That doesn't matter. I can't just put slope equals 4. I have to be like, this is my evidence and this is how it's related. The value of t. All right. And the acceleration vector. See that? All right. And then last but not least, the x coordinate. This is fundamental theorem. It's at time 2, it's at 7, and I want time 1. So x of 1 is, now look, I leave this 2 up to 1 and I make it plus. They've flipped it and made it minus. That's fine. Integral answer. Remember, I made that mistake earlier anyway. Okay. Right. That was back to parametrics. Here is the polar one. All right. Because we are over time anyway. Okay, so I want you to notice they gave you the R equals, but y'all, they drew it for you and they said 0 to pi. So you don't have to worry about any of that crazy stuff we did earlier. You have to know the formula for the area bounded. All right. You have to know the rate of change of the x coordinate with respect to theta. That means I have to write it in parametric form and find x prime. Okay. Find dr d theta at 5 pi over 7 and explain the meaning of your answer in context. All right, that's the rate of change of the distance from the pole. And that's, you know, is it moving towards the pole or is it moving away from the pole at 5 pi over 7? The particles traveling along this polar curve, its position is x of t, y of t. We've already found the x up here in C, such that d theta dt is 3 for all times t greater than or equals 0. Find the value of dr dt at the instant, this is the slope, no that's not, excuse me, rate of change of r at the instant theta equals 5 pi over 7. This is dr dt, not dr d theta. This is implicit. It's a very, all this is so messy. And you're like, Miss Cash, what the heck? Well, they want dr dt. Well, r is in terms of theta, not t. So when I take the derivative with respect to t, it's going to be 0 plus cosine 2 theta times 2 times theta prime. That's where this big hint comes in right here, times theta prime. All right. And then you plug in theta is pi over 7, and that's all you do. Let's look over here. Okay. So here's the very simple area problem, gets you 2 points. All right, don't forget your 1/2. If you did forget your 1/2, you'd still get the integral point, but you wouldn't get the answer point. The second one, you have to x coordinate at -1, so you have to write the x coordinate, which is r cosine theta equal to -1, and then find the answer. Find the rate of change of the x coordinate with respect to theta at pi over 7. So you take the derivative of what you found in B in your calculator, and there's that one. And then D, Find DRD theta. All right, so derivative at 5 power 7 is negative 0.445. Okay. All right, and so since DRD theta is negative, the curve is getting closer to the origin at a rate of 0.445 when theta is 5 pi over 7. All right, and that's because at 5 power 7, it's positive. Okay, and then the particle's traveling on a polar curve, and its position is blah, blah. All right, so here they want implicit. Do you see what they did there? They want implicit differentiation. So something that kind of hints you here, you know, you have dr dt. They gave you d theta dt. All right, that's the hint that it's implicit. So chain rule gets you a point, and the answer gets you a point. Whew. All right. So on reflection, I'm hoping you have gone up on your 1 to 5 scale, and I'm sorry that I ran over. All of these, most part of the PowerPoint and the entire packet are from the National Math and Science Initiative review materials. Advanced Kentucky is an affiliate of the National Math and Science Initiative, and I do work for them, so that's where that comes from. Trying to stop my share. So any questions, I'll be happy to stay a little bit after if you have any, or if you want to go over those FRQs. I'm sorry I rushed them so much. Or you can shoot me an email and I will answer anything you have. Anything else? Sorry, it was so quick. All right, on April 24th, you get Brian Passwater, who is a rock star calculus teacher, and he's going to talk about convergence. So lucky you if you want to do that on April 24th.
All right.
Anybody?
Thank you, Ms. Cash. Here's all the emails if you all want to snap a picture of that. You can reach Advanced Kentucky at advancedkentucky.com. I'm at Marshall at kstc.com. Aaron is the high school equivalent of what my job is.
Yeah,
Previous.
that was a lot.
And Miss Cash's email is there if you need her. So thank you, Miss Cash. Thanks for everybody for joining us today. And again, we hope to see you with Brian Passwater on April 24th.
Are we allowed to email for the solutions to the problems in the packet? Yes, if you send that to me, Sina, I will send you the solutions. So here, I'll send you, so you all can copy. It's amy.cash at, bgreen.kyschools.us. There's my email.
Thank you, everyone.
All right. Okay, Michael, do we have anything we need to do?
No, I need to stop recording.